Hello and welcome to EngPhys 3004, lectures 18 and 19. We're going to be starting chapter 19 with these. So this is going to be the first half of chapter 19. We're going to do 19.1 through 19.4. This is forced convection. So now we're looking finally at, in the convection heat transfer equation, the rate of heat flow per unit area is equal to H convection coefficient times the temperature difference between the surface and the free stream. We're going to look at where this H comes from and how to get it. So it turns out in reality most of the time H is not known except through experiment, and even then it's only 15% accurate. This chapter again is how to determine H and the things that affect it. 19.1 Physical mechanism of convection. So if you know the temperature distribution of the fluid, you can determine the convective heat transfer coefficient through the conduction into the fluid there. This is because convection is really just conduction plus fluid motion, and at the surface interface, whatever heat is flowing out of that surface is the convective heat transfer. But the heat flowing out of the surface is flowing just through conduction, since the no-slip condition means the fluid at the surface isn't moving. So you can say that the convective heat transfer per unit area must be equal to the conduction heat transfer per unit area. So negative K, this is the thermal conductivity of the fluid, now not of the solid, but of the fluid, times the temperature gradient in the direction away from the surface. So this lets you solve for what the convection coefficient must be. If you somehow know the temperature distribution in the fluid, or what the gradient is at the wall, then you can figure out what the convection coefficient is. This is going to be something that we're not calculating directly, but you should keep it in mind because it's going to help you get a feeling for how the heat flow from the surface, how the convection coefficient should be different under different situations. Usually we don't want the convection coefficient at exactly one point, although that's not always true. Usually we want the average convection coefficient over an entire area of interest, over maybe the entire interior area of a pipe or an entire surface of a plate that we're convecting from. So we want the entire heat flow from convection, which is H times the total surface, T minus T infinity. But if the convection coefficient is different at different parts because the temperature gradient is different, or maybe the surface temperature is different, then we really want an average H over the entire surface, the one that's going to be appropriate to use in this formula, possibly using the average temperature at the same time if the temperature itself is not constant. So anyway, we should average this value over the area. Using, just substituting in an average formula, you can see that this formula above would transform into this one. If you've averaged over, this is maybe for something which is length L in the direction of the flow, perhaps. The relative importance of convection is characterized by the Nusselt number. This is another dimensionless number, H LC over K. Now this probably looks identical to the BO number, but it's not the same as the BO number. So the biggest difference was that the BO number was characterizing how important conduction within a solid is to convection at its surface for the purpose of determining whether you can use lumped system analysis, whereas the Nusselt number is convection in a fluid divided by conduction in that fluid. So this is not the thermal conductivity of the solid, it's all fluid properties in the Nusselt number. The characteristic length is defined potentially differently depending on whether you're looking at external flow or internal flow. For external flow, it can actually be kind of similar to the one for the BO number. So the big difference is the thermal conductivity, referring to fluid properties rather than the solid properties. This new dimensionless number is again characterizing how important convection versus conduction is within the fluid. So a high Nusselt number will tell you that the fluid motion is a big deal because the convection is a lot higher than you would get from just conduction, whereas a really low Nusselt number would tell you the fluid motion is not that big of a deal. The fluid is basically just behaving like a conduction medium. Okay. 19.2 Thermal boundary layer. Remember when we talked about fluid motion that the boundary layer was the region around a solid, around a surface, that where the flow of the free stream is being affected by that surface. So we said that the edge of the boundary layer is where the flow has become 99% of what the free stream flow was. So past that, it's basically just the free stream, and we have no idea in that fluid that there is a surface around. It's not affected by the surface. But within the boundary layer, the fluid flow is affected by the surface. It would be slowed down to be closer to the surface velocity, which is 0 relative to the surface. For thermal boundary layer, it's the same kind of idea. Imagine you have a fluid that's moving in at all the same temperature, T infinity, the free stream temperature, and then the surface is all at the surface temperature, Ts. As you move away from the surface, the temperature of the fluid is going to be affected less and less by that surface temperature. So at some point, it basically is just the free stream temperature still, not affected by the surface at all. The point where the temperature becomes 99% towards the free stream temperature compared to the surface temperature, which would be this one, Ts plus 99% T infinity minus Ts. So that would mean that you're 99% of the way from Ts to T infinity. That would be the edge of the thermal boundary layer. So the thickness is given the symbol delta T, and this is a construction that we're going to imagine for thermal versus momentum boundary layer. So while flow is still developing, so that the boundary layers are growing, which could mean that the thermal boundary layer is not completely developed, it's not the max size it's going to be, or the velocity boundary layer is not the complete size that it's going to be. As long as one of them is still changing, then the flow is still developing. Which boundary layer is larger depends on the dimensionless Prandtl number. This is the ratio of molecular diffusivity of momentum, which is the kinematic viscosity, to the molecular diffusivity of heat, which is our parameter alpha. So substituting in the definitions of both of these, the densities cancel, and you end up with dynamic viscosity mu times Cp, the specific heat capacity, divided by K, thermal conductivity. So a Prandtl number of greater than 1 would tell you that momentum is transferred more easily than heat, whereas a Prandtl number of less than 1 would be heat is transferred more easily than momentum. So for this construction, where you've got fluid coming in at a free stream temperature and hitting this plate here, a high Prandtl number would mean that the temperature doesn't transfer that quickly away from the plate. So the thermal boundary layer would be thinner than the momentum boundary layer. You've got a situation where the plate is not affecting the temperature of the free stream that quickly, whereas a low Prandtl number, the temperature of the plate can be affecting a fair bit of the free stream, so the thermal boundary layer would grow more quickly. Typical values of the Prandtl number are plotted in this table. So liquid metals have very low Prandtl number. That means their thermal boundary layers are going to be quite a lot larger than their momentum boundary layers. Heat transfers quite a lot faster in the liquid metals, mostly because of the high thermal conductivity. Whereas on the other end, you've got dense oils. These objects don't transfer heat very well compared to how well they transfer momentum. They're much better at transferring momentum. So you'd have a much thicker hydrodynamic boundary layer, momentum boundary layer, velocity boundary layer than your thermal boundary layer. Right around the middle, you've got gases, and depending on the temperature of water, can behave like that too. So gases typically have Prandtl numbers close to 1, which means the boundary layers aren't that far away from each other. Now, most of what we're going to do for the rest of the chapter is going to be determine the Nusselt number. So the Nusselt number, again, is the convection coefficient times a length scale divided by the thermal conductivity. And we're at times going to be distinguishing between the local Nusselt number, the Nusselt number at a specific point, which is related to the convection coefficient there, and the what you might call the global Nusselt number, or the Nusselt number over the entire area. Now it's a little bit misleading because this is not actually the average of the Nusselt number. This is the Nusselt number which uses the average H. So because of how they're related in length scale, this is not exactly the average of this, but the h in this is the average of the h in this. Okay, so the point is we're going to be looking at figuring out one of the Nusselt numbers, because the Nusselt number is what we use to find h, and the Nusselt number is the thing that we have formulas for. It's dimensionless, so we have formulas which are more widely applicable. They have less parameters in them by making plots of Nusselt number versus other things than h directly. So what does the Nusselt number depend on? If you have the Nusselt number, you can get h. So this is kind of like saying, what does h depend on? It depends on the geometry. It depends on the Reynolds number, because that affects the fluid flow. It depends on the surface roughness and turbulence in the free stream, which also affects the flow character, whether we've got turbulence or laminar flow. It depends on the parameter, the Prandtl number, so how big the hydrodynamic versus thermal boundary layer is. It depends on fluid viscosity variation due to temperature within the flow. That one's pretty complicated. But again, anything that would be affecting the way that heat transfers, the convection properties, could affect the Nusselt number. And it depends on the boundary conditions, whether you've got constant heat flux from a surface or constant temperature at the surface. And all of the turbulent results and most of the laminar ones we get are experimental. So regardless of that, we're still going to have relationships that we can use to figure out the Nusselt number, and that's how we're going to get the convection coefficient. All right, let's get right down to brass tacks then. 19.3, parallel flow over flat plates. This is the first set of geometries that we're going to be able to figure out the convection coefficient for. So this is flow past a flat plate like we did in chapter 15. You know that the Reynolds number grows as you go further along the plate until you reach x critical. The flow is laminar, and then it becomes turbulent past that. And the local convection coefficient, the local Nusselt number defined using the local convection coefficient, is given by this these sets of formulas right here. So in the laminar regime, you can say that the Nusselt number at location x, which is h at x times x divided by k, x is the distance from the start of the plate, is 0.332. Reynolds number at x, this is the Reynolds number using x as your characteristic length, to the power of 0.5 times the Prandtl number to the power of 1/3. And this is valid as long as the Prandtl number is greater than 0.6 and the local Reynolds number is less than 500,000. If we are at a higher Reynolds number regime, but not too high, and as long as the Prandtl number is less than 60, then you could use this turbulent region formula here. So again, Reynolds number is the Reynolds number using x as the characteristic length, and Prandtl number is mu Cp over k as usual. These are designed to be used with the film temperature to figure out the fluid properties. So for both Reynolds number and Prandtl number, you're going to need fluid properties like the kinematic viscosity, the dynamic viscosity, specific heat capacity, and thermal conductivity. And these depend on temperature. So which temperature should you use? Well, these formulas are designed to be used at the film temperature, the average of the free stream, and the surface temperature. So you find that, you find out what your fluid properties are, and then you find out what your Reynolds number is at the location you want, and substitute into an appropriate one of these formulas that depends on the Reynolds number to figure out what the Nusselt number is at that spot, and then solve for hx to figure out what the local convection coefficient is. If you plot these formulas, then you'll see that it gives you a local convection coefficient which goes to infinity at the front end. That's because the boundary layer is infinitesimally thick there, and then drops through the laminar region until you get to the critical Reynolds number, when it spikes up at the start of turbulence and then decreases. So this is what you actually see due to the extra mixing that happens in the turbulent region. Even though the boundary layer is thicker there, you have a higher convection coefficient. How does the thickness affect the convection coefficient? Well, thinner boundary layers mean higher convection coefficients, because if we go back to the physical mechanism of convection that we started with here, the convection coefficient is based on the conduction right at that surface. And if the boundary layer is infinitesimally thin, then the temperature gradient must be really high. So if you wanted to capture that heat transfer phenomenon using convection, to just say that it's some constant times the difference between the surface and the free stream temperature, then the convection coefficient at that spot needs to be really high to capture that information. So most of the time, we're not really worried about that really high convection coefficient at the start, because we want the average convection coefficient over some area. And that means that we need to take the average of the H in these previous formulas. And that's what these sets of formulas are for. So if you are still in the laminar region, the average over some distance L is going to give you a convection coefficient defined by this global Nusselt number, which again is not the average of the previous Nusselt number, but it's the Nusselt number using the average H. And the global Nusselt number is 0.664 root of the Reynolds number using L instead of X, times the Prandtl number to the power of a third. For turbulence, we have a similar kind of formula with a different exponent and different coefficient. And if you are not so far into the turbulent regime that you need to correct for the laminar regime at the start of it, then it's probably better to use this combined formula. Okay. If the Prandtl number is outside of these outside of the ranges, then these relations won't work. So there's a different set of relations that you need to use. So here's your local Nusselt number, and you need to solve this for H and then average over the plate to calculate the actual Nusselt number if you wanted that. But you probably just want the average of the convection coefficient anyway. So to obtain H, just to summarize, you find the film temperature and use it to get the fluid properties. You find the Reynolds number. You find the Nusselt number using one of the above formulas, depending on your Reynolds number and Prandtl number. And then you finally find your convection coefficient by solving from the definition of Nusselt number. Unheated starting length. This is going to be a modification to the formulas that accounts for kind of a common case where you have the velocity boundary layer developing first and then the temperature of the surface kicks in later. So this might be the case if you've got maybe the edge of a table, and then a little bit onto the table there's a hot plate, right? So maybe the hot plate is really thin, so it doesn't increase the thickness, but suddenly you've got a temperature change as you get partway past the leading edge. So the velocity boundary layer starts developing first, and then the thermal boundary layer starts developing within a partially developed velocity boundary layer. In this situation, we've got this Greek letter xi showing us the unheated starting length, and you can use these convenient formulas to figure out what the local Nusselt number is under these circumstances. Now there's a different formula depending on the temperature boundary conditions. These equations are for a constant surface temperature, but if instead of a constant surface temperature you have a uniform heat flux, then you have to use these second sets of equations here. So uniform heat flux means that there's a constant amount of heat coming from each different part of the surface. And so that's these equations there instead. In either boundary condition case, the average heat transfer coefficient is related to the one at L through this set of formulas. So these ones, you'll notice, don't use the Reynolds number or the Prandtl number, but they are based on what the convection coefficient is at x equals L. So first you find the convection coefficient at the L that you want using one of the appropriate ones depending on your boundary conditions and your flow regime, and then you substitute into one of these formulas to translate that into the average convection coefficient. Now in the version of the book that I have, there's a typo in these last equations. It looks like they still depend on x, even though you're substituting in an L at the end, and that seemed kind of ridiculous. So you can verify for yourself that it should actually be xi divided by L rather than x in these equations by taking the integral. Here's some code to do that and show that it works out. Again, it works out that H is the average of Hx, but not that Nusselt number is the average of Nusselt number x. 19.4, flow across cylinders and over spheres. So flow over cylinders and spheres involve boundary layer separation, where the fluid boundary layer leaves the surface, and that means that we're not getting anywhere analytically. So here's some experimental results. Okay, so local Nusselt number varies with angle from the stagnation point, that's from the front of where the fluid hits a cylinder, in kind of a complicated way. So look at these plots. You've got starting Nusselt number here, and then as you move around from the front, it drops and drops and drops until some point where it starts to rise. And then if the Reynolds number is higher, the same thing happens, but eventually you see that it rises kind of extremely and then drops and then rises again. So what's going on in these pictures is a complicated interplay between laminar, turbulence, and the wake region. Just to remind you about some properties that are going on in the laminar flow region, you have a separation point which is earlier than you have in turbulence. In the at the separation point, after that you have a wake region where there's a lot of intense mixing. So you'd expect that things would locally increase in the wake region. You'd have more heat transfer from that extra mixing. Also, turbulence is a lot more mixing than laminar flow. Where does turbulence start? Well, it starts once the Reynolds number gets to a high enough amount. So when we looked at the situation for flow earlier, we said that 200,000 was about the transition to turbulent flow. And looking at these are just kind of at the cusp of this transition region of this critical Reynolds number. So below that, you don't necessarily have turbulence, but you can get towards turbulence as you move far enough around the cylinder. So none of these are turbulent at the beginning. They get to turbulence eventually. And where they get to turbulence is where you would have the extra separation point. So looking at these laminar flow ones, as you move around, you start to get to a separation point, then you have extra mixing, stays laminar, but you got this wake region, so the convection coefficient starts to rise. But these ones are at high enough Reynolds number that once you form the wake region, what actually happens is that lateral mixing kicks everything into turbulence. So the onset of turbulence really spikes up the convective heat transfer and manages to delay the separation point until further around the cylinder, when you have another increase in the convective heat transfer coefficient from the extra mixing beyond the turbulent mixing that shows up once you get into the wake region. So at the end of the day, after this analytical calculation, most of the time what we're interested in is the average convection coefficient over the whole cylinder surface, and that would be the one defined by this average or global Nusselt number given by the Churchill-Bernstein equation. And for this equation, as with flat sheets, what you want to use is the film temperature, the average of the surface and the free stream temperature when you're evaluating fluid properties. Now, if you're only going to be looking at a small range of Reynolds number or Prandtl number, it's probably better to use an approximate relation, which just says that the Nusselt number is C times Reynolds number to some power times Prandtl number to some different power, where the power of the Prandtl number is a third, and the coefficient in front and the Reynolds number power are given by a table. So the convenience of this table is that the formula is a little bit simpler than Churchill-Bernstein, even though it's not going to be quite as accurate when you're dealing with a circular cross-section cylinder, but at least it allows you to do something for these different cross-sections of cylinders. Now, flow over spheres is the last thing that we're going to talk about here. Flow over spheres, average Nusselt number for flow over spheres at a uniform temperature is given by the Whittaker correlation. Now this one is, so spheres are a little bit simpler. We've got just one formula for that rather than the plots and different charts. But one thing that is different is the Whittaker correlation uses the free stream temperature for everything except for mu-s, which uses the surface temperature. As with anything with flat plates and all the stuff that we're going to deal with after, the point is find the Nusselt number using one of these complicated formulas, then use that to find the convection coefficient, and use that to figure out your rate of heat transfer from the temperature difference.